waiting for people to stop finishing. Okay. Okay, welcome everyone, and I have the pleasure of presenting to you Andrea Antonello, who is, let's say, an external member of our team, at least for the time being. We're trying to make him fall in love with Bilbao, so he will move here probably in a few months. But we'll see about that. He actually lives in one of the nice parts of Italy, so he has good reasons for staying as well. Anyway, so Andrea has been an important figure in the open source movement, particularly for what concerns spatial modeling and GIS, etc. for a long time. I knew his name for centuries. And at some point, with my great surprise, he actually, I think I asked the questions online at some point, he answered, and then he eventually, he was aware of what we're doing, and he actually expressed interest in collaborating, which was amazing to me, because my story as a hacker, developer, etc., is being by myself and just doing everything by myself, and nobody understanding what I do ever. So that was a pretty amazing thing, and it led very naturally to him being here today and having worked with us and collaborated with us for quite some time. At this point, we had a contract last year, so it was 1 year of collaboration that produced some more water models, and we're now renewing our collaboration, and we hope to continue for the foreseeable future. So Andrea's experience is mostly in, he's an engineer, and he will tell us something about himself. He has been working with open source GIS for a very long time. Everybody who knows what GeoTools, OpenGIS, UDIG, etc. If those things are known entities to you, Andrea has been part of that, and they exist thanks to his contributions as well. Today, he is going to talk about the parallel track of tooling for spatial modeling and hydrological modeling that he has been developing for a long time. It's called the Hortonmachine, and people who are familiar with this kind of things to know what that means. It's a very established set of tools, which, thanks to his interest in our work, we are now proceeding in parallel. So the Hortonmachine provides algorithms for ARIES and k.LAB and our own work to use and to basically complement the semantic functionality with the spatial modeling functionality, particularly what concerns spatial GIS models and hydrological models. So I leave to Andrea to continue. It will be a bit of a technical seminar, so if you are not a technical person, it may get boring, but if you are a technical person, I promise it will be very exciting. Thank you, Andrea. And
thank you very much. I'm happy that I didn't put my presentation page. I really forgot. I usually do that. But his presentation was way better of myself than I could have ever done. So yes, I have a little company in Italy, but I also work for the Free University of Bolzano. I'm lecturer in advanced dramatics, basically. And yes, I've been, I think, for the last, and this kind of figured it, it's kind of 20 years that I work on this stuff. And when I started, the Hortonmachine was a project of the University of Trento that was mostly geomorphology and hydrology. And in 2002, after graduating, I started to work with Professor Rigon to try to make it more fruitable. And the fun thing is that at the beginning, it was a library written in C. And when I started, we started to bring this in Java, which at that time was an upcoming and promising language. And so when we started it, it was called JGrass. And fun enough, the first collaboration to do this JGrass was with people from Jamaica. So when we started the JGrass project, people were asking what exactly J would stand for and what exactly grass would be. But it was actually just this grass is like the biggest and oldest GIS. It's written in C, and we wanted to kind of be an interface to grass. This didn't work out well, and so in the in the following like 20 years, we tried to find our place somewhere. And the natural choice was at the time to try to end up inside a GIS. So we tried different things like entering UDIC. For us, the important thing was to stay open source. So it was UDIC and at some point GVSig because the language was the same. But in between, we still followed that thing that was so important for us to create shareable models. For us, it was very important to be able to stay in our domain, create models in our domain, but then be able to link them to, we were basically geomorphology and surface water. We wanted to have the possibility to link them to, I don't know, atmospherical models or link them to underground water models. And so we entered a couple of frameworks, let's call them like OpenMI, which is a modeling framework that claims to be able to link together models in different languages and from different research centers. Well, we tried a couple of years and it didn't work out that well. And after that, another one, OpenMI started in Delft in Netherlands. And the second was OMS, which is based in Colorado, the Colorado State University, and is backed also by the USGS. That's another modeling system. And every time we tried, really, we integrated, we made a big migration and integrated it. But in the end, we couldn't get really a good grip around these integrations. We were never able to link them together with other stuff. And as he actually told around 2019, a couple of years ago, I got a question, well, could you upgrade the Hortonmachine to a new Java version because we would need, and we started chatting and I found it funny and we had a nice chat. And after a while, I looked what this integrated modeling is because I didn't know of it. And I thought, well, that's why we made the Hortonmachine. It's now a couple of years that we don't migrate into something. We should really try again to migrate into something and lose time in this because it's really a huge effort when you do this stuff. Okay, and actually, when we started to chat and work together, I figured that we would not have to migrate anything because it would take a couple of lines of code to just simply make them available inside k.LAB. And I want to show you later how, maybe with his help. But first, I would like to show you what the Hortonmachine is right now, if you think of it just alone. Our dream was to be able at some point to have it just as a library that you could place somewhere, which now at this point is k.LAB, but that at that point we didn't have that, so we needed something, and that was mostly GIS. But at some point, when we were in GVSig, people from QGIS said, yeah, how can we use your models? And we were like, yeah, okay, it would be in GVSig. And they said, yeah, I do not open QGIS to use your models. And I can also understand that kind of. And what we did is we extracted it as a standalone application. And that made it kind of simpler to be used by normal desktop people. And it looks more or less like this. The image on this screen is not very nice. You can't read almost anything, but you have something that is a spatial toolbox, as there is one in QGIS, as there is one in ArcGIS. And in this spatial toolbox, you have a huge set of morphological and hydrological models. That's what we started with. But time passing, we added a couple of raster and vector tools. And then there is a whole branch that is dedicated to digital field mapping. I did my PhD on digital field mapping, and in that, I developed first something that was called geopaparazzi, and would be something for field survey. So you can create your forms, you can create your teams, and go out surveying, and then come back and synchronize your surveys to a central server. After that, since a lot of people, mostly Japanese, were saying, in Japan, geopaparazzi is a bad word. Couldn't you change the name? And I said, no, oh, sorry. No, geopaparazzi is a cool name for an application. But people were telling, yeah, we are never, when we bring this to our administrations, to use it for surveying, and we say, yeah, we want to use geopaparazzi. They were like, what? And that was working only on Android. And that at some point we decided to do a version that also would work on iOS. And at that point, we decided to choose something with a bit more, let's say, a name with a weight. And that would be the smart mobile application for surveyors' happiness. Smash. And luckily, around the Hortonmachine, there are also the University of Bolzano, where I'm now lecturer, was interested in working on forestry models. So we have a whole part that is dedicated to LiDAR data, extracting stuff for forestry. So very quickly, the Hortonmachine modules, there are a lot of stuff that you probably know if you do hydrology by computer and you use ArcGIS or QGIS. So drainage direction, total contributing area, this should be something that you do all the time, extraction of watershed, of networks. Then there are other hydrological attributes like rescale distance and some type of curvatures that are dedicated to hydrological models. And in that case, this could be things that you don't find in other toolboxes about hydrology or geomorphology. Regarding statistics, we have two main models. One is the kriging which actually is in work to be fast because somebody in k.LAB was complaining it's slow. And then there is another, which is the JAMI, just another meta interpolator, which is an interpolation for those models that need variability on the vertical. So it could be temperature, pressure, and wind. These are a couple of the tools about statistics. This is the main hydrological model for the calculation of the maximum discharge. It has been used a lot also by our local administrations. And it works both with a statistical input, like rainfall, intensity duration curves, but also with real events. So you can kind of calibrate it and check your results. The result is actually, well, the peak that a particular basin would throw out for a certain rain in which time, as you can see, for different return times. If you're in hydraulics instead, there is not so much, but there is something. One is the one-dimensional hydraulic model called Saint-Venant, which takes also inputs and outputs, but it's one-dimensional. And then there are tools. If you're in hydraulics, you probably use HECRAS. The problem of HECRAS is preparing the data, because if you use hydraulics with GIS and you have your river networks and that stuff, and you don't have everything already prepared, there is a module that can export, take in shapefiles, DTM, and that kind of input data and output something for HECRAS, just to be able to run a model. This is for hill slope stability. It's called ShallStop, and it gives you critical rainfall and the stability in the various parts of the basin. We have one model that works with debris flow. It really generates the cone of debris, the fan of debris, and it works by generating the triggering, the propagation in the network, and the final propagation on the fan. It's based on a Monte Carlo algorithm, and as you can see, this is the real and the simulated outcome. It's a simple but quite powerful model. The last thing, very quickly, is LESTO, this LiDAR Empowered Science Toolbox, open source. It's basically a couple of modules to do extraction from LiDAR data. So the first thing you need if you just have LiDAR data is being able to have also your elevation model. So if you don't have, you need an elevation model that is compatible with your LiDAR data. Because if you work on forestry and you have slopes, particular slopes, it's difficult to extract trees if you don't normalize everything. So there is a module to do that. extract the elevation model, some tools to extract buildings from LiDAR data, and tools to extract trees to calculate biomass. And this here is different from the usual models in that it does a single tree extraction. So it identifies the single trees, and it gives you an idea of the crown of the trees also. Okay, I didn't want to go in this introduction, give you more than that. I really wanted to also try to give you a little hands-on workshop just to show you how things can be done. On the slides, but I will run over this here now. I hope the slides will be made available. You can find how to install the tools that I'll be using. And it will have some how to install requirements, how to do the first run of your scripting console, because even if it might scare you, a console, if you're a modeler, a scripting console is something extremely powerful and will help you a lot to lose less time while you're doing the models. That usually when you start doing them, they just come out wrong. So you need to understand why they are wrong. And this kind of tool can help you a lot. So let me see. I also inserted here an example that I usually show because it's understandable by people from more or less any science, which is how to extract. Let me run over this. How to extract certain attributes from watershed. And so here you would really have a step-by-step that you can follow to do, starting from the digital elevation model, just how to extract flow directions and the total contributing area, how to then, well, do some styling on them, and how to extract the network based on different parameters. And all this today, I will not show you this because in this particular context, it makes more sense to have a look at what interests you most, which is a water yield model. So I think I will jump out of the scene here and I will finish this presentation. Just so you know, here you can, you will find a couple of things to do network extraction using the scripting console, which gives you the possibility not only to run it, but also if you have more, more files to work on, you can execute a lot of stuff in batch mode. This is what scripting is also very powerful at, but not only. So if there are questions on this part, I can answer them now. Otherwise, I will move over to do some real-time water yield model and show you how this console could work. But I think this was just introduction, so it should not be difficult to get a grip around. All right, so water yield model, and should I turn this a bit here? Okay. So water yield model, I prepared a little script here, just the first part, which is some imports you need to do, which the language needs if you want to use certain models. And then I have an input folder that contains the input data that you need for water yield. There, the global water yield is composed, that we will see, is composed of 4 models. The first is you calculate on your basin the runoff. After that, or in parallel, you calculate the evapotranspiration on your basin. With those information, you need to calculate what happens with infiltration. So there is a module for infiltration. And finally, you can calculate your base flow. So in the end, you have on the whole basin, but usually you're interested in the closing in the outlet of your basin. In the outlet, you could have the information of the base flow and the runoff. So with these 2 information, you get the information of the discharge, which is basically what we want to understand. So these are the inputs you need. And the first module we're going to use is SCS. So how do I know if it's the first time I look into this, what kind of syntax to use? Because that's the problem with most of the tools. If there's not a lot of documentation, it's very difficult to start with it. And luckily, the spatial toolbox actually is this thing here, and a normal user would simply use the models from here. But if you want to chain them, you have to use the console. And that's what we're going to do now, because it makes more sense for us to create a chain and check the intermediate results. So we can look for run off here, and we will find a module that's called SCS runoff. We see that it has a couple of inputs, it has an output. What we can do here to get some help is we can say, we create a new, it's called SCS runoff. And that's how you build a model. You build this little model, and you have two helping methods. One is really help. You cry for help, and just to make sure that you run the model, which is this button here, or yeah, you run the script, which is this button here, or Ctrl+R, and it will give you a little description and stuff. So the module is experimental, the authors are the k.LAB team, and usually if somebody writes team, it's because it's not documented well, so nobody will know who did this. And you have description of the input parameters. This helps, but is not really what we need, because what we need is a template. And if you run this, you can just select it and copy and paste it in here. And this makes it easy to just say, okay, rainfall. We have an input map here. It's my rain. This is just the input folder, and I just attached the name of the file. I should just to show you, this is my folder. I have this input files, and then I have an output, which is currently empty. So I can just say input is rain. The in network is my stream presence. It's where I have network and where not. The map of curve number, CN, I named it CN. Number of events is events. And then there is my output. The output discharge is something new. So I can say it's my runoff, and it stays in the out folder plus, let's call it runoff.tiff, because it's a raster with the value of runoff in every cell, clearly. So out folder, this should work. And once I set all my inputs and outputs, I can call process, which will just launch the model. If I run this, it will do some stuff, and I can check, sorry, here, it generated a new map. What you would do is you would load it into your GIS and then check if the data are right and this kind of stuff. But while you do modeling and you prepare your little script to also do some digging of information if the results of the model are not right, because think this as a moment where you are writing a new model. Well, you can do something here, like there is a class that allows you to read the raster file, let's say the runoff, and just it gets a format. It checks on the format if it's a TIFF, an ARC grid, or whatever, and it returns you a layer. And with this layer, we can then create a little map object that can have a width, if you want, width of 1200 and a height of 1000. And then I just add my layer there, and this would be layer. And then I can say, oh, display my map. And if I run this now, it will show me the map without, it's actually, it's not visible, but in here you have a projection, and it's, if you overlay other kind of data, you can also check if the result is actually geographically correct. This is also something I would use. Sometimes in k.LAB we have issues with projections, so it might be a good idea to first, before you run to someone and say it's not working, k.LAB, you can check this and overlay your data here. If there is a shift here, since it uses the exact same libraries, geographic libraries as k.LAB, there might be an issue actually. Not in k.LAB, but maybe in the underlying libraries. So one thing you could do just to make it a bit more visible, you can add a style, and there is a style for color table, I think. And you can choose, maybe let's call it blues, a color table of different blues. This takes a minimum and a maximum, and you can define also a transparency. If you want to overlay several layers and check them visually, then you can use the transparency. One little issue here is to define the minimum and the maximum, but the layer luckily has something called get extrema. And get extrema returns you a dictionary that contains some extrema, as the name says, the minimum. Since it's rasters, it could be a multi-band raster, it could be a satellite image or something. So you have also to, it will return a list of minimum and maximum. So you can say, okay, give me just the first band. And very quickly, let's do the same for maximum. And I will keep this little piece here because every time I change, I create a new map, we will just have a look at it. So let's see if this works. Okay, this looks already a bit better. One thing that you might notice or not from there is that the runoff model is very much influenced by the rainfall. And in this case, we took the rainfall data from Copernicus, and the resolution is very, very low. And so if you work with this on a small basin, you will have square patterns based on the rainfall. All right, so this is about runoff. The next one, well, exactly the same way, evapotranspiration. This is more difficult because it's potential evapotranspired water volume. That's when you potential evapotranspired water volume, hopefully. Template. Okay, I've been lucky. Let me just pick this. So crop coefficient is one of our input data. It's Kc. Then I have minimum, maximum, and atmospheric temperature, which is my max T. Min T, just T, then I have some solar radiation. These are all input data that you will need to find if you want to work with this. It would be possible to pass in also the reference evapotranspiration, which is calculated basically from all the other quantities a part of the crop coefficient. So this is not necessary right now. And then we have a new output, which would be, just copy this over to be quick, the potential evapotranspiration. So let's just put it here and we can just run. So this would be the next module to run. So here we're talking about evapotranspiration. Let's make this red. This looks a bit nicer because it's based on the crop coefficient, and that one has a higher resolution. So it's not influenced yet by rainfall or stuff like that. So as we run on, we produce I don't know why I have this open. We produce the different inputs here. You can also generate the color table automatically for QGIS if you prefer to every time open up or load them and or remove them from your GIS. And this is how it works very easily. The next one would be infiltration. Infiltration is infiltrated water volume is a more difficult model in that it also considered the upslope cells. So there's infiltration going downwards, but also moving out of the basin. So infiltrated water volume, as usual, I use my template trick. And if I don't want the stuff after that to work, I can just remove it. Okay, so potential evapotranspiration, well, we just created it at the step before. Then this also needs rainfall. It needs the map of flow direction, which we have and we called flow. It needs the network because infiltration on the network will be just null. And then there are a couple of parameters and intermediate maps that are generated that we basically added because while we were developing the module, well, at the beginning, it just didn't work. And we didn't understand why propagation would not work. So we just printed out some intermediate stuff. The only parameter which is necessary is the fraction of the upstream recharge during a year, because this model was taken into consideration a year, and we made it work on any time span. So what you need to put here, if you're considering conceptually a year, you have to put here 1 divided by 12 because it's the monthly recharge. And then we have 2 new outputs, which would be the infiltration and the net infiltration. Let's call it like this. And again, you just add net infiltration and infiltration. And let's have a look at what infiltration looks like. Okay, this kind of makes sense. It bases on rainfall, and it is 0 in those places where you have a channel network. So you have this kind of map. We are almost there because what we want is put together all this information and bring it down to the outlet. And that is exactly what the base flow module does for you. And that's the last one. Base flow water volume. Base flow water volume. Perfect. And here it takes as input the infiltration we just generated, the net infiltration, the network, map of flow direction, and then it can produce several outputs. Again, here some are necessary and some not. The base flow is actually that thing that we wanted to calculate. So let's create a base flow output map. Base flow. And let's also plot the base flow in blues. Okay, this kind of makes sense. if you're into hydrology geomorphology, this kind of looks like a total contributing area map, as any map that propagates stuff from the basin to the outlet, from all the parts of the basin to the outlet. In these kind of maps, it makes sense often to use a logarithmic visualization, because when you accumulate, the outlet value is very high and you have very low values in the source cells. So if you want to have a more, well, actually we could use, I think, the color table for the total contributing area, which is a more relaxed logarithmic map. And this gives you exactly the result you need to know. It gives you a good idea of how the water goes from the external parts of the basin down to the outlet. If you also need to have the final output, I hope I remember that properly, it gives you also a number, because usually you would like to know if you close a basin in a particular outlet, you just want to know in that particular point what the amount of water is. So it could be outlet discharge, and that would be one of the outputs QB of the base flow module. Let's see if it works. Yeah, I can move it away. So it will give you also the output discharge. The fun thing of this kind, if you're not used to scripting, it might be, you might be thinking, why should I use a tool like that if I can just drag and drop stuff into a GIS? But believe me, when you, when you use this kind of tool for a while and you're doing modeling, if you're just producing single map stuff, use a GIS. Absolutely, I agree with you. But if you do a lot of modeling and put together different stuff, this at a certain point makes you way, way quicker than anything else. And obviously here, maybe you don't use this, but you use k.LAB. It can make sense sometimes if the results in k.LAB of your model do not work. That's what we did. We went back a moment to the console and we tried to script and to understand where the stuff is. Let me see if I remember. There are tools in here that also allow you, I don't know, maybe I show you later if there is time, because what I would like to show you now is how this actually integrates inside of k.LAB. Because one thing we agreed on when we started to working on these modules was that the actual logic of the single knowledge of infiltrated water volume, of the runoff calculation, of whatever is necessary would be inside the Hortonmachine. But then it should be used from k.LAB. And some of you saw this already yesterday, but the resolution is really terrible here. You can't read a thing more or less, right?
You can double click the window so it fills the screen, and then you can use Control+ to enlarge the font until it's readable.
Ah, beautiful. Okay, so this is the water yield model in k.LAB, and I think maybe Ferdinando can give you the point of view from the side of k.LAB, because he would do it.
Up to you. If you want me to, I can do it. Otherwise, you can.
No, you do it. I think you have a better workflow on whatever is contained. I'm a bit too fast on these kind of stuff, a bit too technical on the hydrological thing.
But it's two dimensions of the problem here, really. I keep losing pieces of myself. The interesting thing about this is that you saw, I mean, Andrea did all the groundwork, and it has a process, and it has broken down the problem into its components, its logical components. So in order to do water yield this way, which is a simple way to do it, but it can be done all over the world, and it's the way that invest, for those who know what it is, does it. Normally when you want to do this kind of modeling, you have to start like he did, putting together data, creating files, all in the same projections, all in the same grid size, etc., putting them into a directory, writing the places where they are, etc., etc. And it is great because in the end, that's what you need to do if you follow the process technically in the engineering way of running a model. You know the model, you give it an input, you get the outputs, you use the outputs. It's all totally fine. k.LAB is meant to skip those parts and just use semantics and artificial intelligence so that the work of the modeler that he showed you, and it's important to know how to do that, can be done by a machine, by just mentioning, by just using the concepts that actually mention and describe the problem that you want to solve. So this is the example of how we write the semantic annotations, as we call it, for the models that you just saw. So the models you just saw are here. Basically, when I say using here, this basically points back to the Hortonmachine. And we are using a lot of the models of the Hortonmachine. By the way, we're not using all of them, and it's a pity because there is a lot of stuff we can use, and we should discuss how to use the entirety of it. Because at this point, the two projects are kind of, brother projects. So it's really good to see that one uses all the possible elements of the other. But what you see over here is a completely different kind of code. And this is the language that we use for k.LAB, which is called KIM. It's knowledge integrated modeling, which is models integrated by knowledge. And basically everything you see here is knowledge, is concepts, which refer to known ontologies, basically to documents that describe each of these concepts, so that you can, for example, color code. Model evapotranspiration, which is red because it's a process. Within hydrologically corrected watershed, this is the most important thing. Those models need to run in a watershed. If they don't run in a properly delineated watershed, they produce only a mess because the model cannot assess where each drop of water falls, because it will fall out of the boundaries of the map that you're using. So if you do it on a rectangular region or on a country, which is composed by several watersheds, but they don't cover the country exactly, they may go outside, etc. A decision maker needs to know all these details, so they cannot do it directly. Why? By just saying that evapotranspiration is a process that we need to compute within a watershed, and a particular kind of watershed, because it needs a bit of a correction in order to work properly. Here, we just attach a model to this part, to the watershed, so that when we ask for evapotranspiration, the program automatically knows that it needs to build a coverage of watersheds, and within each of the watersheds, which is the operator within, which is a logical operator, just stating the problem and nothing else, not saying anything about the how, it knows that it needs to distribute this model through watersheds. And when that is done, if the person who is actually asking for this result has asked for this result in a country, the system will, by virtue of this definition, take all the watersheds in the country, run the model in every watershed, and then merge the results and cut them up so that they reflect the country. And this is all done automatically. And that's the point of k.LAB. It makes it simple for scientists, for non-scientists to actually ask scientific questions. But it also makes it very simple for scientists that are different scientists to ask questions about a science that is not their science. And that's why it's an integrated modeling program. So if I am a social scientist, I know exactly how to compute certain social things, but I know nothing about how to compute water pollution. And water pollution needs to compute water transport, and for water transport you need hydrology. So if you can ask questions logically, like in these models here, then you can integrate models because you don't have to worry about the details of the how, you just worry about the what. And each person who knows about the what of a particular problem can put something like this online, so that a machine can find, the same way that you find something in Google, you look for, you want to buy a car and you look for cars in Google and you get a description and where to buy them and how much they cost. Here you need to know about potential evapotranspiration, and you type here potential evapotranspiration, you know nothing about it. The system goes on the network, finds these models and computes it for you, and then it will go back to your model, which knows how to compute these things using this as an input. And that's the spirit. So if you look at these models, each model is very short because, first of all, it doesn't worry about the technical details. That technical details, you just saw it happening from there, but you state your outputs. So this is the model of evapotranspiration that also produced the evapotranspired water volume, which is a different color. This is a process. This is the quality, something that you can measure. So evapotranspiration creates a volume of water which is evapotranspired, and that's your likely result of interest. And in order to compute that, which is basically the semantics for the inputs that are needed, the stuff that Andrea was putting file names for, here, instead of file names, you just state what you want logically. So I need the maximum atmospheric temperature in Celsius. I need the crop coefficient, which is another concept. I need the atmospheric temperature, which is not either the maximum or the minimum, and it's not the average of the two, so it's an independent input. You need the solar radiation. I want it in megajoules per meter cubic meters per day, and you say nothing else. You don't say about where to find it. You don't say anything about where to find the files or how to measure it, etc. You just say that you want this, and this will go online and find whatever it needs to do. So for each of the modules of the Hortonmachine that compute water yield, and it's just a small part of the Hortonmachine, and this is a very small part of ARIES, you see that there is a model here that base flow, wet calc, etc. Each of those things are connected but also independent. So you can compute each one of these. And if you want to not compute the model, not know anything about the model, you go on the Explorer, which has a query bar, and you write runoff water volume, and maybe you can do it. And you will see that the system thinks for you and just start computing stuff. And in order to do that, the first thing to do is to realize that in order to compute a runoff water volume, you need watersheds. So it will find the watersheds that are needed in order to answer that question. And then within each watershed, and it's doing that right now, there is a model about watersheds in the network, and it's now found it, and it's now building the watershed structure. So once the watershed structure is there, then within each watershed, it will call the runoff module for the watershed, which requires precipitation, etc., etc. I hope it's doing it.
Yeah, I think I chose a quite large area.
That is true. It's probably taking all of Spain and most of France.
Yes, exactly.
But maybe it's fine. Give it a second, because.
Però adesso si blocca.
No, non necessariamente si blocca, però sì, forse è meglio fare una cosa. Magari uno di quei test cases, però ormai hai fatto partire, sarà difficile. Sorry, I speak Italian every now and then.
Yeah, I have
it's actually doing
this.
it already, so it's not necessarily a bad thing. It needs to compute at least one of them before you see the watersheds, so there is little fun in there. But as you can see here, these are the outputs of the Hortonmachine. This is k.LAB, but the outputs that the Hortonmachine is printing, will be printing in the console over there. It's now capturing them and printing them as outputs of k.LAB, and it's basically the same way that we integrated the Hortonmachine. We integrate a lot of other software that is offline. We don't always have the fortune of being able to work directly with the providers and the developers, but pretty often we are able to see that now watersheds are there. So maybe you can start showing that on the screen. And they are pretty big.
Yeah, we wanted to show how powerful this is.
Well, that's pretty powerful, because normally when you run a hydrological model, and this is a legitimate hydrological model, you have to work quite a bit. Here you just have to say, I want the runoff, and that's what it does. And all this information doesn't come from one place or from one machine. There is no data on that machine. There are no data in most of the machines that actually can use this stuff. But what's happening now is that it's computing an enormous double hydrological model on 3 watersheds that cover most of 2 different countries. And all of this, it's not a very high resolution, and the resolution is chosen by the system, but you can obviously force the resolution you want. Good luck if you choose 5 meters, this kind of thing. The other interesting thing is that the watersheds have been chosen based on the extent that you're interested in. Now, that's a crucial point, because if you choose a smaller extent, your definition of what a watershed is different, because watersheds are composed of other watersheds. So you can have the minor reaches of the rivers that merge into larger reaches, etc. Because Andrea took about half of Spain as a context, the system realized that in order to model the water in that big resolution, in that big extent, it needed to consider the entire river network of Spain. But if it was like the tiny Vizcaya part, it would probably just have taken the Nervion watershed, and that's the way this works. So now it's still working because it is computing just the initialization values of those models for each watershed independently. And what you can see here is that it's taking the first initial data. So this is the elevation data with the elevation color map. This is the curve number.
Yeah, exactly.
Curve number, which is kind of nice to look at because it's very happily colored, but it's basically reflecting the runoff and infiltration potential of the, depending on vegetation, soil type, and this kind of stuff, etc. And as soon as it finishes initializing, we will see the bar here will start moving, and it will take a long time, I'm afraid. But it means that first it initializes at time 0, and then you use actual temporal data. So by default, if you ask a question in k.LAB, it will focus on the year before the current one. So now it's going to give you the entire dynamic runoff for all of 2020. But obviously you can change those assumptions in the way you want. But by default, it assumes that it will want you to understand things at the level of the latest year that you have full observations for, on a year scale, and on a certain resolution that basically gives you a decent map and a decent resolution to work correctly for those algorithms to produce sensible data. And I'm not sure if we should wait, because waiting for this one will be pretty long, but we could do the same examples, but
we could show the data flow, maybe.
Oh yeah, sure.
Because that one is quite cool.
Yeah. So this is it's not totally perfect. There are a few things that should be connecting actually. They should connect to this.
Probably it's too big.
No,
too much.
It's something that is missing from the definition of the adapters. It's my problem about it. But when the system has finished computing a model, this is not one model. These are several models connected, because as you saw before in the conceptual definition, the color of the code, each model specifies its inputs logically, and it doesn't know if those inputs will come from data or from another model. So in the end, all the decisions that are made build what we call a data flow, which is basically a flowchart of the actual code that the system will follow. So the artificial intelligence builds the model for you. You only give it components and parts. And for the k.LAB representation of scientific reality, a model is either data or calculations, but it's still a model even if it's data. And that is correct, I think, also philosophically, because data are gathered and measured with certain assumptions in mind, with certain resolutions, etc. Data are a model of reality, simply evidence-based instead of calculation, computation, hypothesis-based. So we use the same keyword in k.LAB to annotate data models. We say model, and that's it, because that's what it is. So when that is done, a data flow like this is built. It's probably using the developed version that has some bugs, so not everything is connected, and you should normally see these boxes lighting up when the system is computing certain things. But anyway, that's what it is. And at the same time, if you show the report, maybe I don't know if there is any report to show here. No, that's not this one. But when we write models for public consumption, and this one is not ready for public consumption yet, The system also produces documentation, which is basically in the form of a printable report with introduction, references, etc., by collecting all the pieces of documentation for the other, for each component and from the data, and compiling a report which can be printed and given to a decision maker, and the details, all the details of the computation. The same happens for data sources and all these kind of things. You can see that over here. So that's basically the gist of the integration in k.LAB. k.LAB is basically another layer on top of the, you know, let's say the business layer that he has developed and been talking about, and uses the semantics as the trick to do the integration that Andrea was discussing before. Andrea and his partner, business partner, did a lot of work trying to integrate these models inside pipelines that could make it easier for people who are not specialists in hydrology and GIS to use those models from outside. And they always failed because nobody had ever done it in a way that is this simple. I always thought that the only way to do it is to
the third one was missing. I understand why.
yeah, I think it would take half a day.
Well, already the fact that nothing did explode, I think.
It does it. I mean, it will do it. It will take the time it takes. But the only thing that we cannot see
is the temporal.
No, it's a temporal, because before it gets there, it's going to have to do a lot of
stuff.
The other part that would be interesting to see is that the context that Andrea had set was just this square region. Could have been a country or something else. And now the interesting part is that if you take the square region and the decision maker asks the question about runoff in that square region, not in those watersheds. What happens is that in order to compute runoff for that square region, you need to first find out all the watersheds, the complete watersheds, then compute the runoff in them, and then build a coverage of the runoff in that square region, because that's the result of interest. So the fact that you can automate that kind of decision, but by simply saying within a watershed in a logical model, is quite amazing, because otherwise you know how much work it is to just take all this data, merge them together and give them. And in this case, there is no human involved, because all this part of the basically the labor is kind of not very difficult, to the point that the machine is completely capable of doing it. But if you don't use semantics, there's no way the machine can do it, because you can actually, you know, it can program it in. But this kind of stuff only happens reliably and in completely generic contexts if you build a semantic mechanism that can actually parse your intention as a logical statement. And then from that intention, build a workflow that can actually compute the data. So that's basically why the two parts of this process are so well integrated, because he knows how to do it, and I know how to put it together. And together we can build tools for decision maker that might take 2 hours to compute, but still it's a lot less waiting than having and money than having to pay a hydrologist to do this for you, because they will ask for a lot of money. So that's more or less what I want to say about this. Do you think there's anything else?
No, I think as usual you made the point.
It would be nice to stop it, but I'm not sure about this.
No, because it's the thing is, it's now pulling Copernicus data of half of Europe,
right,
and interpolating them to be usable. So
yeah, it's probably going to take a little.
Yeah.
And normally you have that button over there that you can stop computations, but this is very distributed computation, and it's not very easy to stop it.
Yeah, no, I think it's still. Just very quickly, yeah, I think, I hope at least it is clear how for us that we're have been like creating tiny little models for the last 10-20 years. It's really a pleasure to see something like this, because every time we have to do, our tools are more, you know, for the local hydrologist that gathers the data at the local administration. then puts them together, and then the resolution doesn't work, and then how do I do? And then they do the reproject, and the squares are not, the cells are not square anymore, and stuff, patterns appear, nothing works, and then you do this kind of stuff. But actually the Hortonmachine was born with the hope that at some point it would be on a really global scale. When we started, our motto was, our line was all in a GIS, because for us modeling the world, the most logical way would be in a GIS. Now I could say all inside k.LAB, and for us seeing those models inside k.LAB and being able to just, well, maybe not run it on whole Europe, but just focus on a watershed, look at a particular region, or even better, you have a region and it takes 3 watersheds, computes them, cuts them out, and gives you the final result in exactly that part. This is quite something if you're in that field. And the same way, I assume every other science that is doing modeling will have the same fun in here. I don't know if before we close, it's already 1, if we're able to show you something.
Maybe I can say a few other things so we can wait a little bit more.
Okay, yeah, just say to it's almost there. And
one of the other good things about this approach is that it gives a much longer life to the products of science, like models and data themselves. And I think that's one of the most horrible things that happens these days, because data are produced at enormous rates. And for every problem, there is a guy or two or a girl who write a model and takes like 2 years to develop in debugging, and then they use it twice and then they throw it away. And that is so common. It's incredibly. It's become the standard way of basically doing science, is spending an enormous amount of time to solve one problem and then starting from scratch the next time. Now, this thing is something that gives a much longer life to things, because you can reuse data for purposes that you haven't envisioned when you got the data. You can reuse models because they become parts of modeling chains, and they can actually be prioritized. So your model may actually be better than another, and nobody will ever know it because they don't know it. But if it's on the network and it's parameterized so that a modeling chain can actually find it and decide automatically if it's the best model for that context, then it's another way to give a longer life and to basically maximize the investment, which is enormous, that you do when you write new models and new approaches. So that's why we build this thing, is not only for solving problems more efficiently, but to keep solving problems with the same resources. And the more you use, the more you contribute to the system, the more powerful it becomes, because all that stuff stays there. It's never forgotten, because it's machines that handle it, not humans. And that's one of the main reasons. For example, just a very simple example, before we can actually see this running, you see that the time is moving over there now, because it's a much smaller resolution and context. So now it's actually computing the temporal slices. But for example, they work on LiDAR. They have this thing that is meant to identify trees, and it's a very nice thing because it does it in a very intelligent way, so you don't get out too many trees for the thing. We use it for mountains. They had no idea when they wrote it. And it's actually turned out to be extremely useful for us, because we do this outdoor recreation models that are supposed to find out all the possible points of interest in a region, and sometimes you have no idea what those are, so we look for the tallest mountains. And it turns out that their software that is meant to identify trees identifies the mountain peaks perfectly, because it's exactly the same problem except a different resolution. So half the world, because it's part of the suite of models that we're doing for the UN, half the world is using that to identify mountains. They use Andrea's software to identify mountains, and Andrea never knew that. I'm pretty sure that I'm telling you this for the first time.
Cool.
So that's what I'm talking about maximizing your investment. It gives a much longer and a much better life to the products of your work, whether you know it or not, which might be the catch. But so as you see there, the runoff water volume is being computed on 3 watersheds for that square region over there. And you can actually already show it probably. So it's the same story as before, except this time is fast. So it's a smaller region and it's a low resolution
Yeah.
design. It's just a test.
Even if you say small region, it's not exactly
Well,
a
it's
small
very
region
small,
if you
but
work on this kind of stuff.
resolution, yeah.
Yeah, I have to wait it to finish, right?
No, you don't have to.
Could
you
I?
You can have a click. You will see no
Yeah.
data. And this is actually right because this is the initialization value. So you see time goes from here to here, but there is an initial situation, right? So elevation is going to exist in that initial situation because elevation is of the context. It pre-exists the time. But runoff, and this is all part of the semantic analysis that you have to do for these models, runoff only is a product of the process of moving water around, so it's a process of precipitation. So it only exists when the time is actually running. So you need to click on that bar, the bar over here, in order to move out of the initialization state, because runoff is no data at that stage. So if you look at that now, you can actually play the movie of the runoff in this region, which is the runoff of the 3 watersheds. So it's computed properly. The points here will be computed knowing that the outlet is over here. And these are all decisions made by the machine just on the basis of having said that this is a model that only makes sense within a watershed. These are very useful results. This is the INVEST model that some of you may have used, the water yield model. Except in order to run it, instead of finding a postdoc that has a year of his life to waste on that, you just click a button.
Okay, I'm happy that we were able to just show also this part. And well, so what is the message for all you modelers out there? Come over and bring your models into k.LAB, because it's really a fun place to have them run. And as he said before, I think for somebody that writes a model, having it run in your own cellar is not that much of fun. If you have it somewhere where really many people can use it, that's one cool thing. But even more if somebody else with from another science uses it. That, in my opinion, that was the idea when we started all this. So I'm happy that after only 20 years, I've been able to find a place where this actually works. So thank you. Thank you for having me today also. If there are questions, I think we...
Yeah, Andrea is going to be here all of today and tomorrow. So if anybody wants to talk to him.
Yes, I'll be happy to.
Thank you.